Hi everyone. So we are the Solar-Terrestrial Interactions team, and I would like to start by thanking our private partners, IBM, Lockheed Martin, NVIDIA, and KX for their endless support and resources. And I would like to thank our mentors, Mark, Monica, Andres, Troy, and Graham and Lika for their support and holding our hand through this journey. And I'm Burcu Koşar. I am a postdoc at NASA Goddard Space Flight Center. I work on Aurora and Lightning.
I'm Bala Pudwal. I'm a heliophysicist from SETI Institute, Boulder, Colorado.
I'm Casey Hanmer. I'm a physicist and engineer.
I'm George Garolas. I'm a computer science, University of Missouri, St. Louis.
Okay. So you might think that you know the sun, and I think you know a lot better after the previous theme. Sun, every day we wake up, we look outside, it shines, it gives us warmth, some of which we can use right now. And, but our connection is actually much deeper than that. And sun is changing every day. Its magnetic activity is actually changing all the time. It has an 11-year cycle. It's sometimes quiet, sometimes very active. And so what happens is, during this activity change time, sun creates sunspots, flares, and all sorts of good things. When its magnetic field gets too wound up, what it does is it gives this magnetic bubble into the interplanetary medium called coronal mass ejections or solar winds. This is like launching a magnetic missile into the interplanetary medium, and Earth's magnetic shield kind of protects us from it in a certain level. But what happens is, as you can see in this animation, it fluctuates, wraps around, forms a tail, and on the day side of the system, when this wave of magnetic bubble hits the Earth's magnetosphere, it's like a bee sting. It can just snap it open, a process called magnetic reconnection, and it can go to the day side and then reconnect. This is the mechanism that transports solar particles into our atmosphere and create a phenomena called geomagnetic storm, or it creates space weather. So some of this space weather is beautiful, such as the aurora, you guys can see here, but some of this space weather is actually really harmful. So it can damage our systems that we take for granted, such as our power grid, because when these particles are precipitated into the atmosphere, they can induce currents, they can affect our transformers. Not only that, they actually can affect the operations of GPS and also satellite operations, and they can affect, the radiation can affect the astronauts that are in orbit, and also our aviation systems can get affected. So what do we do about this? NASA, NOAA, and US Geological Survey, they operate a vast network of satellites that are monitoring constantly the driver of the system, which is the sun, and the impact region, which is the Earth. So what this is, they're collecting this big data constantly. They're well calibrated, they're science quality data that is readily available, and they're open access. So particularly in this study, we are using two different types of data. We are using geomagnetic field data that is collected by instruments called magnetometer on the ground, and we are particularly focusing on 14 stations that are distributed over the continental US. And also, we are looking at solar wind data that is collected by the Ames satellite that is about in L1 orbit, million miles upstream of Earth. And both of these data that we are using they're complex time series data. So where machine learning and AI can help us is, it's tough to extract information when you're dealing with a lot of time series data. Scientists tend to look at things and focus on like one piece of the puzzle, but these systems can help us find relations between these time series data. So we are Project B-STING. So the word B comes from the fact that we refer to magnetic field with the letter B. STING is the Solar-Terrestrial Interactions Neural Network Generator. So that's what we ended up naming our system. It's a data-driven open source tool for space weather forecasting. It predicts a commonly used index called Kp that captures the geomagnetic disturbances. So the value proposition of this, we use open access science data. We combine this with AI and machine learning techniques, which will give us better scientific insights and therefore better predictions.
Well, I guess you remember the word Kp that you mentioned. So what is Kp? And why did we choose Kp for this prediction? Here, what is shown here is a geomagnetic field detected by one of the 14 stations. And the top panel there is the, top panel is the edge component, and you can see there are two horizontal lines that shows the range of the fluctuations detected in that particular time. So Kp essentially determines the range in every 3-hour interval, and then corresponding to the table shown there, it assigns a value. On the left-hand side of that table is the K index assigned, and on the right-hand side is the range of that particular variation in that 3-hour period. So Kp index varies from 0 to 9, and the 0 indicates a very quiet geomagnetic field, that is, there's no activity going on, and an index of 9 indicates that it's an extremely disturbed period. So why did we choose this as an index to predict, is shown here. It explains very well how disturbed the magnetic field is, and on the left-hand side of this this image here is a Kp index plotted over a period ranging from October 29 to November 1st. During this time, there was a famous event, space weather event occurred that is called the Halloween event. And looking at that, you can see that the Kp index is fluctuating or reaching all the way up to the extreme level, that's 9, and it remained there very disturbed geomagnetic field for an extended period of 3-4 days. So that indicates how, that's a single number that tells you how disturbed the magnetic field is and what could be expected from that disturbance. In contrast, on the right-hand side is another plot that shows that K index remained below 4, which indicates that it's a period of a quiet time. Again, these Kp values are assigned to the geomagnetic disturbance level. On the left-hand side again is the active geomagnetic disturbance level. It goes from G0 to G5, corresponding to a Kp value of 4 to 9. And on the next column, it also terms or gives a name to the activity level below storm, moderate, and extreme geomagnetic storms. Further, it is also can be associated with the level of space weather impact. Here's a list of some famous space weather events that occurred during the past several years, and starting with the Carrington event that occurred in 1859. That's an extreme level of space weather event, and this can be, if you look at the previous level, extreme event corresponds to a Kp index of 9, and that is the G level geomagnetic storm. So there is a direct connection that can be established between the Kp values and the level of geomagnetic activity, and in turn the space weather level, the event level. So we chose Kp index primarily because we are using the high latitude geomagnetic data, and there are many other geomagnetic indices available which require low latitude data, which we are not using at this moment. So where does the machine learning come again? As we said, we are dealing with 500,000 data every year. So that is something that is beyond the power of human intervention, and that is what we that's why we decided to go with machine learning.
Thank you. So we began this project with a bunch of ideas in mind, and over time developed the ones that seemed more promising and, let's say, killed the ones that did not. And today we're going to present to you 2 of these projects. But these projects use more or less a common data source. We've got geomagnetic and solar wind data and also some data on the KP index. And then we also used a range of publicly available packages developed by experts. You know, in 8 weeks we don't have time to completely reinvent the wheel on neural networks and stuff like that. So as you can see, we used Keras, which is a Python wrapper developed quite locally for TensorFlow, which is Google's open source a deep learning kind of platform. And we developed most of our code in Python, and we also used the scikit-learn library to perform some kind of basic, some prediction stuff. So starting with project 2, which was the KP index prediction effort, we used a range of standard statistical methods that are available in scikit-learn. And this was initially attempted as kind of a baseline, but it worked too well, so we're actually talking about it today. And then project 1, which I'm about to talk about, was an effort to produce vectorial predictions of basically every single data set we had at arbitrary points in the future using LSTM or long short-term memory neural networks. So there hasn't been a huge amount of talk today about long short-term memory neural networks or neural networks in general, but the really cool thing about these, as opposed to say the convolutional neural networks that are used for image processing, is that these contain some memory. So if the state of the current situation is hidden, such as whether the sun is angry or not, that can be in some sense encoded within these neural networks and remembered from one step to the next. So one way of thinking about this is that the X0, 1, 2, and so on are a time series data set, such as the Australian dollar to US dollar exchange rate, and then, just as a random example, and then H0 through H1 is the output of the neural network, such as what that exchange rate will be tomorrow. And then you can train this neural network by putting in data and then getting what it comes out and comparing that and then applying standard neural network training techniques. And then once the training is complete, and there's many, many ways of doing this, it's kind of like herding a large number of hyper-intelligent cats. You have some leftover data which you haven't trained on, so you haven't kind of contaminated the validity of your training situation, and you can run that on this and see if you get results out that seem good. And one of the really neat things about this is that it kind of abstracts away like the detailed physics that I spent the better part of a decade in higher education learning into the computer. And so you don't have to be particularly explicit about these interactions. If they exist, there's some chance that the neural network will pick up on them. There's also a good chance that it won't. You know, I'm not the only person in a 5-mile radius who's deeply confused about the precise limitations of neural networks to capture this sort of information. So on the left here, we have a chart of the flow speed of the solar wind recorded by the ACES satellite in a week in the middle of November last year. I trained the neural network on this data and some other data sets, kind of January through September-ish, and then tested on the last part of the year. It's just one way of dividing up the data. And what I was attempting to do was to predict the flow speed 3 hours ahead of what the current data set was, and this is with minute-by-minute data, so it's 180 minutes into the future. And the blue line is the real data, and the yellow line is the predicted data, and you know, there's a couple of glitches there. But I was kind of surprised by how good this was, and I still am. So that's kind of a cool thing. One way of rationalizing what's going on here is that the data that's going into this, the data that talks about what the flow speed is, actually has structure in it. You know, there's a lot of physics lying underneath there. You could compress that data. And what the LSTM is doing is finding a useful way of compressing that data so that in the future it can tell what it's going to be. And the chart on the right is a graph that compares the accuracy in terms of the relative least squares error of a persistence prediction using the same algorithm over a range of times. I've got logarithm of the time base 10 on the bottom, so from 1 minute on the left to 6 hours on the right. versus the LSTM prediction, which is the yellow line. And so that kind of shows that the LSTM's prediction is capturing data that, capturing structure in the data that persists for at least 6 hours. Now, I would love to spend another year digging into the finer details of exactly what this can do or what it can't do. But I think the final bit of serendipity I'll point out is that I was attempting to predict BZ on the Earth, which is important for induction of geomagnetically induced currents, using information about BZ, the vertical magnetic field in space, and the solar wind speed. And what I actually found was that I wasn't really able to predict BZ on the surface of the Earth very well, but I was able to predict BZ in space and the solar wind in space using data from the Earth. So that's kind of cool, I guess, but understanding why that is and how much more data needs to go into it is a different matter. One of the really cool things here is actually, if you just try and, in the previous chart, these x0s are not just numbers, they're vectors of numbers, in our case maybe up to hundreds of different data sets simultaneously. And as you increase that number, the accuracy of the predictions increases as well. So that's pretty cool.
Okay, so on to project number 2. There are whole books written on boosting techniques, and I'm going to try to condense it down into 2 slides. So up at the top here is what the computer kind of sees as far as the representation of gradient boosting. So we did get some results for gradient boosting, so I'm going to zero in on that right now. But what I want you to think of is, for those who don't understand what boosting techniques are, is imagine you're working on a really, really tough problem and you have one committee. That one committee probably is not going to be able to solve that really, really tough problem. So what you're going to do is you're going to get a number of committees. And when you take a look at each one committee, they're not going to be very powerful unto themselves. But when you combine them, take the outputs of all the committees and combine their outputs, they're basically going to come up with a very, very strong result. And that's the basic idea behind boosting techniques. When you talk about gradient boosting, you're bringing in more of a functional approach on that. So the next slide, just before I jump on to the next thing, when we're training boosting algorithms on the data, we're taking a number of trees and we're training it for one pass on the algorithm. We take the outputs of those trees and use that as inputs for the next generation on training those trees. So the trees are actually going to reweight themselves as they go through the population or evolution of this. So the next slide is going to give you a visual representation of that. So if you can imagine each click, it looks like this is sort of jumping around a little bit. Each frame is the tree reweighting itself on each generation of it's learning at this point. So as it's going through each frame, it's readjusting itself to a better solution. So this would be the analogy of committee members or people in committees basically giving their answers at progress meetings. And they basically share knowledge and they come up with a new configuration to come up with a problem, solution to the overall big problem. This is pretty powerful, and we got some very interesting results because of applying this technique.
All right, gradient boosting result. Here is our result. On this graph, we plotted the observed KP index, which is our ground truth, and 3 different models. The green and yellow lines are the mean and median, and the blue dotted dots are the output of that dance that you just saw in the previous slide. After all that beautiful dance, this is what it gave, and we are pretty happy with this because we see a scope there. It's not it's the best matching. It's very close to the observed one at many places. Well, there are discrepancies, of course, but we were very surprised and happy to see this particular graph. So summarizing what we saw in that previous plot, here is a table that we have compared many other models. The one that is highlighted in green is our gradient boosting. And we compared the models, the numbers are the mean squared errors, and we did that for 1 hour ahead prediction, 3 hour ahead, and 6 hour ahead predictions. And there are, the significant trend seen here is that gradient boosting improves, gave their best result as can be seen from that highlighted green lines. And we can say this, that the gradient boosting is giving the best result with at a confidence level more greater than 95%. So that is our, that's what made our results stand very strong. And here comes the wow moment in during our whole project. The machine learning technique does not know anything about the domain. But when it gave out the results, it gave out the relative importance of the parameters that we have already fed into it that went into the decision making to make the best prediction. So the gradient boosting told us that the most important factor there is the current KP index, and other important predictors or the factors that determine the best prediction are solar wind, magnetic field, strength, and the BZ, solar wind speed, and the proton density. Again, there was another unexpected result, that it also told us that it is better to consider the north-south component of the geomagnetic field at low latitudes, such as Guam, Hawaii, and Puerto Rico. Traditionally, when the space weather forecasters forecast, they consider only the solar wind parameters as the decisive factors for predicting the geomagnetic level. But the gradient boosting method told us to consider another component. These north-south components are related to or associated with the ring current that forms in the equatorial region, which has a very influential impact on determining the geomagnetic activity level. So in retrospect, we feel that this makes really good sense, because we need to consider what additional parameters for the betterment of the space weather forecast. So that is why we think machine learning has a scope in space weather prediction, not only just prediction, but it can give improved predictions. That is our takeaway from this.
Okay, so just to wrap up, what I mentioned earlier is that we have this vast network that is collecting big data for us that is science grade and high quality. So we utilize some of this data. And what we did is we developed a tool using state-of-the-art AI and machine learning algorithms that can predict the geomagnetic index, KP. And this made us understand, like this tool with its predictions, it made us do cross-validating the physical assumptions that are traditionally used in scientific research. And not only that, As a scientist, it really excites me is that these algorithms can extract important physical parameters without a priori knowledge of the system. And this is really exciting to me because I see a lot of potential in it. During the problem definition phase of this project, because of the complexity of the system, it was tough for us to adjust our focus and reduce the dimension or the amount of that data that we have that governs this complex system. So there is a lot of potential. And I also want to add that our framework is available on GitHub. It's an open source Python module pretty much for heliophysics data analysis. And I want to end by saying, to me, this is just the beginning. I intend to continue working on this because, as I said, looking at the complexity of the system, there is a lot of data that we can ingest in, and we might be able to find some hidden correlations or connections that we missed as just by looking at from a different, like, fixed focus. So that's pretty much it, and thank you for being here and listening our presentation.
Thanks, guys. Amazing work. I never thought I'd get goosebumps looking at a KP index plot, but you did it, so thank you. So our reviewers, please jump in. Any thoughts?
Yeah, it was a very nice presentation there. In terms of predictive capability, you're looking like 3 hours ahead. I guess there's two things. One is the ring current was very interesting that you found that in that case. But in terms of 3 hours ahead, essentially the earliest probe you have is only about an hour ahead. So, and you found that the biggest parameter, the most important parameter was persistence. So how much of that 3 hour prediction is really just persistence rather than ring currents or solar wind? That make sense?
Could you please repeat the question?
Yeah, well, it's several questions muddled together there. But one of them is how much of your predictive capability was really a persistence forecast? It looked like, like you said, the predominant thing was the current KP index was the biggest predictor. And the second part is, if you took that out, how far ahead could you really look? Because your earliest sensor is, unless you're sort of predicting something that's ahead of the solar wind, you're only seeing about an hour into the future, as far as your earliest sensor.
If I understood the question correctly, if we don't include KP, we could still predict the KP index up to 6 hours with the same confidence level.
Sangram.
Fantastic work. As you said, it's just the beginning, but a lot of promises ahead. Actually, in the previous presentation, I was mentioning about the STMs, which is good to see here. A couple of things. Did you guys try like a simple, straightforward, variational Bayes kind of uncertainty assessment on the STMs?
Sorry, I missed the word after Bayes.
So it's almost like Bayesian recurrent neural nets just to do an uncertainty assessment on the predictions?
I was very paranoid about the LSTM fooling me, and it did more than once. And there's no guarantee that it hasn't yet done it still. But the thing I was most worried about was the persistence issue that you touched on earlier, which is that if you're sampling something with a periodicity of, say, an hour every minute, and you merely repeat what you last heard, you'll be 96% of the way there. And so I actually performed a cross-correlation with artificial time delays to find out, like, okay, great, we're doing a good job of predicting now, but is it actually just doing a really good job of predicting what happened a minute ago? Like an even better job. And I found that with this data, although I helpfully didn't produce the graph, it was actually centered where it should be. It was actually producing a prediction that was most salient on where it actually should be, which was reassuring. Does that answer your question?
Yeah, kind of, actually. This is good to know. One more question I had is, this comes from the signal processing background, kind of, because we are looking at non-stationary signals most of the time. And when you do like a time frequency localization, you could actually reconstruct a signal for a specific frequency because you're looking at different periods, right? And I think it's a good kind of technique to apply in this case. So you essentially reconstruct a time series based on the particular frequency you're looking at, and then apply a prediction algorithm, because your uncertainties will probably shrink a lot.
The thought did cross my mind. My basic understanding of those techniques is there's a linear transformation from, say, a time series data to some kind of inverse space, inverse time transform, a Fourier transform, or a Q something or other, or some sort of a wavelet transform or something like that. The thing about the linear transformations is that they are that's the one thing that neural networks do really well. So my assumption was that if something like that turned out to be important, the neural network that was being trained kind of with me being blind would just figure it out on its own. Cross fingers. But I was, my experience doing PCA, for instance, on gravitational wave signals a few years ago kind of illustrated the futility of taking a Fourier transform and then performing PCA. It's just linear plus linear is still linear.
Perhaps one more comment.
So yeah, I think I'm kind of still amazed at both the approaches, the solar air forecasting, solar-terrestrial connection, where what we are seeing, what you have showed essentially, that machine learning is pulling out actually real physics parameters. You're not feeding it into the system, but it's giving you as an output. That itself is actually pretty significant, I think, in terms of also kind of unearthing physics for future. So it's fabulous. I had a question about this one, in that you've taken stations that are covering not even quite half of your magnetic field in terms of Earth's magnetosphere. So if you were to sort of take the entire set, global set, what changes might you anticipate? Does this bias what you're doing in any way?
I'm just going to get the first part of that question, which is about capturing physics. So while it's true that the saliency kind of results from the KP index prediction and so on shows that the machine learning has captured some of the underlying physics, I wouldn't call it the same thing as physics per se, because it's not unifying in a sense. Understanding the LSTM understanding the underlying magnetic field of the sun or something does not allow it to predict how to make an electric motor, as an example. And for the other part?
So what I think is, if we can just extend this work using the data from the magnetometers that are distributed all over the world, I think it might actually give us a lot more information, I think, about the system, I would say, because we're focusing on just the northern United States. And what I also think is that it's not, what is really fascinating me about this particular application that we did is that it's not necessarily what we found is because correlation does not always mean causality. So what I really found in value is that this can lead us look into these things and try to understand if we are actually missing anything. So as a scientific, from the scientific perspective. So that's what I think. We might even discover more things by expanding this research and looking at a larger constellation of data from different magnetometers. That's, yeah.
If I may add a little bit to that, it's again, even LSTM, I think the scope of that approach is that you could try different input data and then see, and also try to predict different output and see which of these input data are really necessary to produce what you are looking for, as an output. So that is something we haven't explored yet. We have only started with the geomagnetic data and the KP index and solar wind speed, but there are a number of other kind of data that can be used. For example, the geomagnetically induced currents or the ring currents, as the gradient boosting has already mentioned us to look into. So these are different possibilities that are still somebody, or even as anyone of us, can look into.
I'd like to just add just one extra part to this. Data wrangling is a really, really intense issue. So getting the data from one agency, we weren't able to get clean data. So we had to go to another source to get data, but even that data itself, we had to scrub a lot. So there's a lot of data preparation, and this is just for geomag. When we add in other sources, that it takes a bit of time and storage, but it's important, and it'd be nice if there was, speaking as a computer scientist, if there was one repository for this data, because the data in of itself is a product that's kind of spread out amongst agencies in various formats and various cleanliness and various file formats. So that's kind of a tag-along issue for this. That would greatly help out science aspect on this.
Thanks, George. On that note, unless there's any other closing thoughts, I think you all agree that was phenomenal work. Thank you so much. I once did a presentation that predicted that an AI would make a discovery in 2050, but it looks like you guys have done it a bit earlier.